MiniMax Sparse Attention by the team at MiniMax. We are jumping right into it today because this paper solves the absolute quadratic nightmare of running ultra-long context windows at actual deployment scale.
Oh yeah, it's a total game changer.
Right. So the core insight here for you listening is that they built a Blockwise Sparse Attention mechanism directly on top of grouped query attention, or GQA. And they use this really lightweight, entirely X-pre-index branch to retrieve only the top K key value blocks per GQA group.
Yeah, and then the main branch executes a KV outer sparse attention kernel.
Exactly. And the hardware level wall clock speedups are just staggering. Like on an H800 GPU at a 1 million token context on a 109 billion parameter mixture of experts model.
Which is massive.
Totally massive.
Yeah.
This architecture delivers a 28.4x reduction in attention FLOPs, gives a 14.2x faster prefill, and a 7.6x decoding wall clock speedup.
Wow.
And it does all of that while completely matching the performance of a dense GQA baseline across, text, math, code, and multimodal benchmarks.
It's honestly a massive technical flex. I mean, for everyone listening, you know that everybody wants a million token context right now. You need it for agentic workflows, repository scale coding, all of that.
But standard softmax attention just melts the GPUs.
It literally melts them.
Yeah.
So the mission of this deep dive today on AI Paper Slop is to unpack exactly how MiniMax took this theoretical sparsity and translated it into actual hardware-level speedups.
Without nuking the model's actual intelligence in the process.
Right, because to understand how they got that 14.2x prefill speedup, you first really have to look at the architectural split.
The decoupling.
Yes, the split that makes it possible to bypass the standard softmax bottleneck entirely.
So break that down for us.
So it's a dual branch system. They basically split causal attention into two distinct branches. You have an index branch.
Which is the part that figures out where to look.
Exactly. And then you have the main branch, which actually does the exhaustive reading, the what to look at.
Okay, so let's look at the mechanics of that index branch. For each incoming query, this indexer is scoring key value blocks. And the block size, which they call BK, is 128.
Right, 128 tokens per block.
And it scores them using max pooling, and then independently selects a top K subset for each GQA group. And in their setup, K is just 16.
Yeah, just 16 blocks.
So to put that into an analogy for you listening, think of the index branch as a hyper-efficient paralegal.
Oh, I like that.
Right. So instead of the senior partner, who is the main branch in this case, instead of the partner reading 10,000 giant legal files from cover to cover to find one precedent, the paralegal just quickly scans the labels on the file cabinets.
Yeah.
And the paralegal hands over only the 16 most relevant folders. Then the senior partner does the deep, exhaustive reading, but only on those 16 folders.
That's a perfect way to think about it. And a really critical engineering detail here is that the paralegal, the index branch, it basically operates for free.
Because it's X-free.
Exactly. Softmax is an order-preserving function.
Right.
So if you just need to find the top 16, you don't actually need to calculate the maximum or do the exponentials or sum everything up.
Which is where all the compute usually goes.
Yeah, all that overhead is just gone. The index branch just ranks the raw scores. It completely skips the max, exp, and sum steps, keeping the overhead incredibly low.
Okay, but having a smart architectural split is great on paper. But if your memory access patterns are scattered all over the place, your GPU is going to stall anyway.
Oh, 100%.
So how did MiniMax actually extract this kind of performance from H800s? Because you can bypass softmax all day, but if you're waiting on memory bandwidth, you're dead in the water.
Right, so this is where the hardware co-design comes in. And it's honestly the most fascinating part of the paper to me.
Yeah?
Yeah. It's all about beating the GPU scheduler using KV outer iteration.
Okay, unpack that.
Normally, your attention kernel iterates with queries on the outer loop. You grab a query and you scan across the keys and values.
Right.
But MSA completely flips this loop. They do a KV outer sparse attention forward pass.
Wait, I'm trying to visualize this. Gathering scattered queries to match a specific key value block sounds like a huge memory management headache. Why would you go KV outer instead of standard Q outer?
It comes down to the arithmetic intensity math.
Okay.
If you do Q outer, your FLOPs to IO ratio is roughly equal to G.
And G is the GQA ratio, which is 16 here.
Exactly. So 16 FLOPs per byte of IO. which is terrible. You're completely memory bound.
Your tensor cores are just sitting there starving.
Starving. But if you flip to KV outer, your FLOPs to IO ratio becomes roughly 23 times the block size, BK.
Oh, wow. And BK is 128.
Right.
But that ratio shoots up to almost 3,000.
Exactly. You instantly become compute bound. What they do is they pack the ceiling of 128 divided by G-query positions together, along with their associated G heads, all under the same KV head.
Which perfectly fills the 128 by 128 tensor core MMAs.
You got it. It's brilliant.
Okay, but flipping the loop has to create issues with hot blocks, right?
Yeah, definitely.
Like if one KV block is super popular, like a sync token at the start of the prompt.
Right. Every query wants to look at it.
So the thread block assigned to that KV tile just gets absolutely hammered by thousands of queries. How do they resolve that collision without using atomics? Because atomics are slow.
Yeah, they didn't use atomics. They used a two-phase combine and pre-scheduled chunking.
Okay, how does that work?
The scheduler basically analyzes the workload upfront. Since they know one block might be a hotspot, they split the work across multiple cooperative thread arrays, or CTAs.
So they just distribute the load preemptively?
Exactly. It prevents hotspots from forming entirely, and then the secondary kernel just merges the partial results lock-free.
That is seriously elegant.
Yeah, it really is.
Okay, so the forward pass is blazing fast, the tensor cores are happy. But let's be real. Anyone who has ever trained a sparse attention model knows the forward pass is the easy part.
Oh, the backward pass is an absolute nightmare.
It's a nightmare of instability and dead gradients. Because top T selection is non-differentiable. You can't flow a gradient through a hard sorting operation.
Yeah.
So how does the index branch, the paralegal, actually learn what to select?
Yeah, if the language modeling loss can't flow backward, it's a huge problem. So MiniMax solved this with a separate KL alignment loss.
A separate loss entirely.
Yeah, it forces the index branch distribution to match the main branch's attention distribution, but only on the selected blocks.
Wait, if you force the two branches to match, doesn't the tail kind of wag the dog?
What do you mean?
Well, the main model is 109 billion parameters, right?
Right.
Couldn't the main branch just get, dumber to match whatever random noise the index branch is spitting out early in training?
Yeah.
Like the senior partner just dumbing down to match the paralegal?
Yes. And they actually observed that exact failure mode. It's a classic self-distillation collapse.
Oh, wow. So how do they stop it?
Gradient detach. They applied a stop gradient right at the index branch input.
Oh.
So the KL loss only updates the indexer's projections. It acts as a purely local supervision signal.
So the main backbone never sees those gradients?
Never. It completely protects the backbone from gradient spikes and stops the self-distillation.
That's incredibly smart. But you still have a bootstrapping problem, right? Like at step 0, the paralegal is just handing over random garbage files.
Right, which is why they use an indexer warm-up.
Okay, so they don't start sparse.
No, for the first few iterations, about 40 billion tokens, both branches just use full dense attention.
So they just bite the bullet on the compute costs initially?
Exactly. You let the senior partner figure out what it actually wants first across the whole context window.
And then the paralegal learns from that perfect signal.
Right. And once the paralegal is trained up, you flip the switch, turn on top K, and let the sparsity fly.
I love that. And because the training recipe is so stable, it leads to some really fascinating emergent behaviors.
Oh, the emergent behaviors are my favorite part of the paper.
It really is like the death of hard-coded heuristics.
Yes. Let's talk about the natural attention sync.
Yeah, normally researchers have to force the indexer to select the first block.
Right, or add a learnable sync parameter, like in GPT-OSS.
Right. But MiniMax found they didn't need to do any of that.
Right, not at all. They tried forcing it, but the model naturally learned to assign an extremely high selection probability to that initial block anyway.
Across all the layers and heads.
Yeah, almost all of them.
That is just beautiful. It organically reinvented the attention sync.
It really proves that if you give a neural net the right gradient path, it will find the optimal heuristic without us hard-coding a thing.
And it wasn't just the sync tokens, right? What about the group-specific stripes?
Oh yeah, the visualizations in the paper are wild. While all the GQA groups naturally select the local diagonal, meaning the nearby tokens, and the sync tokens, different groups learn entirely different long-range selection stripes.
So they aren't just collapsing to a single global pattern.
No, they are genuinely specializing. One group might track formatting, another might track variables. It's fully organic specialization.
Okay, so we have great architecture, incredible kernels, stable training. But the ultimate question is always the benchmarks.
Always.
Does it actually hold up against dense models? Because hallucinating incredibly fast is still just hallucinating.
Right. So they ran a massive 3 trillion token budget experiment at the 109 billion parameter scale to prove it.
And they tested two different paths to sparsity, right? MSAPT and MSACPT.
Yeah. So both use 64 routing experts and have a strict budget of 2,048 tokens per query.
Which is just 16 blocks of 128.
Exactly. Very restricted.
So what's the difference between PT and CPT?
MSAPT is trained from scratch with the sparse attention. MSACPT is continued pre-training from a 2.6 trillion token-dense GQA checkpoint.
So retrofitting an existing model.
Exactly.
What were the results?
They both hold their own against the full attention baseline. It's really impressive.
Did one perform better than the other?
Well, MSAPT is slightly stronger on math, image, video, and long context retrieval.
Makes sense. It learned the sparse pattern from day one.
Right. But MSACPT is highly conservative. It preserves sheet context and agentic tasks almost perfectly.
Which is huge, because it proves you could take a massive dense model that you already spent millions training and retrofit it for efficiency without breaking it.
Exactly.
But what about the extension test? I mean, push to the limit, like 128K context evaluations on ruler and helmet?
Even there, MSACPT remains incredibly close to the dense baseline.
Wow.
It proves that long context capability is preserved despite operating on a highly restricted attention budget.
So to wrap this up for you listening, the massive win here is that MiniMax has proven you don't need to sacrifice model quality to break the quadratic attention bottleneck.
Yeah, you really don't.
By co-designing algorithmic block sparsity with these hardware-aware KV outer kernels, we are genuinely entering an era where 1 million token contexts aren't just theoretical flexes.
No, they are practical, deployable reality.
Which is just awesome.
It is. And, to leave you with a final thought to ponder here, right now, MSA operates with a fixed budget of K blocks.
Right, 16 blocks every time.
Exactly. But imagine a future where this indexer is fully dynamic.
Oh, like allocating different amounts based on the prompt.
Yes. Imagine allocating 5 blocks to simple syntax queries and 500 blocks to really complex reasoning steps.
That would be insane.
Right. If the index branch can learn where to look so efficiently, the next frontier is teaching it exactly how much to look at, token by token.
That is definitely the next mountain to climb. We will be keeping an eye out for that. Thanks for joining us for this deep dive into the source material. Catch you next time on AI Paper Slap.